hey Codex, we're just starting you on this application. There's another engineer working. We are adding feature splatting here to our repo. So the big work that we need you to do as a sub agent is to take our current renderer, fork that renderer so we have a new renderer that supports feature splatting. Below is the handoff code that we will give to you for that task. You should be able to find the metal shader, copy those metal shaders, add feature splatting, and tell us when it's done and how we can configure it. And then I'm going to do this as just a separator, and I'll copy paste this handoff below. And so now it's got all this stuff, and Codex is just going to cook. Oops, I just merged those two together. Can I put this back up here? Yeah, there we go. Let's go back to Claude and we'll say, okay, Claude, good job. I handed off the feature splatting rasterizer work to Codex. Can you handle the other stuff and make it configurable? And it's going to start coding for us. So we'll see. I think something else that I'm thinking about that I would like to add here is it'd also be great to have a way to visualize these features when we splat them. So I'd like to make an optional value in the config that says render and log features with PCA. And so use a typical PCA approach to take our 2D feature splat when we do these logging intervals and to render the features for each frame and to make a video and an image that is the PCA of the features as well as the ground truth we already do of the RGB video. And then I'm going to say continue your current work and use multiple sub agents. Just going to add some more work for Claude there. So I think I can show you what that is and what I just asked it to do here. Makes a little more sense visually, not text. Basically this thing here, if we look at these features, they're not colors, but they do have some sort of characteristic to them. So we're going to just have them log those alongside the video so we can sort of see what features it's learning. It should. Let's do 2D deep learning feature visualization. Here's a 3D one we can look at. Oh, these ones are not very good. Let me go into Google Images, might find us something. I know. Let's do SAM attention visualization. Feature visualization. Here we go. Here's a cool version of it. So you kind of see what I'm talking about and what we're hoping to get out. So, oh, it's a tiny image. Let me pull this up. ResearchGate thinks I'm suspicious. So these are features. If we look at the bottom here, this would be RGB, which is what we want to render. This would be features. And so each feature is like the inside of the neurons of these things. And so different features will fire for different stuff in unique ways. And so like you can see this one head here and this other head here. This one is like hollowing out for the cow and seems to be red where the motorbike is. It's almost like a motorbike feature. This one seems to be like a car feature up here. This one has like a real cow feature. And so they kind of like, this is the dense representations that learn what is underneath these things. And all these models have different versions of them. And I think C radio features. This paper did some very cool visualizations of what these different features can look like as well. Here's some more dense ones that are a little more descriptive. And so on the left is your image in RGB. On the right is your features. And there's two different models. You can see how they visualize stuff better. And they argue our V4 model is better because on the left, V3 has like all of these little scratchy bits here. And it's like, what are these little dumps and nubs and holes? And Lower resolution, like you can see it kind of has the head with a little bit of hair, but then you're like, wait, this guy doesn't have hair. And so if you look at this one, it's like it's got a very solid helmet shape, kind of pulled out. He's even got his glasses, and you can see his mouth, and his even his tracksuit in this one kind of has like a purple glow and then fades to green, where here it's like there's like a hard cutoff at his sleeve. Pretty impressive that they show these kind of nice features. And here you can really see even better. It's like one feature is the briefcase, one feature is the ball, this feature is the ground. It has a shadow that has a combination of ground plus some shadow. The clouds have a set of features, but they have different lighting on them. The sun off the water has a different feature than that. And each color represents a different cluster of these features. And so the features can be smooth and represent many things at once. And since it's a big vector, it can represent all sorts of things. But also, there is some clustering. And so what we're going to do is use PCA, which is how these are generally rendered, to kind of pull our big 23 vector into 3 different clusters, and we'll render it as if it's a color, and then we'll be able to see kind of videos of what features we're decoding as well. Here's some more dense stuff they do here. And they show kind of how you can use this. And so in their case, they're like, we can even segment out the bikes by just putting in a bike prompt, seeing what the features do, and then clustering on it and stuff like that. Features, the lifeblood of machine learning. Here's some cool stuff with features from this. This is deferred splat paper where they learn normals, diffuse colors. So instead of learning RGB for volume, they learn standard 3D kind of modeling. Will learn what is the base color of this object. So if there's flat light hitting it the same from all directions, what's the color? And then what is the reflectance? So where does the color bounce off more? What is the normal? So what's the like bumpiness of it? Because the bumpiness makes light hit it in different ways. And so they learn each one of these parts that typically a 3D artist would make, and you pass those into a 3D renderer, and then that's how video games look so nice. So they actually learn splats that instead of doing RGB, learn all of these different kind of hand-coded features, if you will. And so what we're trying to do is learn these in a generic way. And so if we look like this, these are all very specific features, but if we can learn a vector that has 23 values that can sort of represent any one of these features when needed, if we render it, it should be able to do anything. That's kind of the idea here. So it's like implicit versus explicit features. Let's go ahead and check in on how our guys are doing here. I think I'm gonna need some like elevator music for this stream when we wait for these guys. It looks like I'm a little worried that it's editing our old code instead of forking it and copying it. But yeah, it looks like it's getting close to finishing. The fork is in place and renamed. I'm patching the bridge to carry feature dim. I'm just gonna ask it. I'm gonna say, hey Codex, I'm a little worried because it looks like you're changing code. I'm hoping you didn't change any of the original v5 because we need that for a baseline. And we only wanted to copy files and fork and change them. Hopefully you did that. I'm seeing things like conditionals where it says if RGB, else add background tail out. And the idea of forking it was that we didn't have to add these if RGB conditionals. We wanted to just do feature splatting and then leave our old v5 to just do RGB splatting. So basically I see this sort of thing and I'm thinking like, uh-oh, why is it doing if else? Because it should only be doing one thing. So I wanted to keep my kind of old RGB rasterizer completely intact, don't mess with it, and then only add feature splatting. And it seems like it's copied it and forked it, so it hasn't messed up the old one, but I think it's trying to do both in one shader. And for anyone who hasn't done a lot of kernel programming, why is this important? Shaders kind of hate branching. So the compiler takes this program, turns it into the program code that runs. CPU code deals with branching better because they're the serial processor and they can do predictive things. They can kind of eliminate branching at runtime in better ways. Kernels, you really want to avoid if conditionals as much as possible. Sometimes they can compile them away. Sometimes it really doesn't matter if you set it up right and it'll run just as fast. But sometimes if you just have two paths in the same kernel, it compiles to like be able to do both of those and use 2 times as much memory or have a more flexible execution path. And it can't do this kind of hyper optimization that you really want on your GPU kernels. So, and this is all running on top of, I have a library that I released recently, which is fast Mac gsplat. And so basically for Gaussian splatting, you need 2 things for your gsplat. So there's the forward and the backward pass. And so if it's just a renderer that's rendering volumes and you're not doing any machine learning, you just need forward, which is like take all these balls and splat them against the 2D scene. So the viewport now has a render and we can see what's there. If you're doing 3D splatting and you want to learn it, you need to splat them, and then you need to learn an inversion. So the way backpropagation works is you say, splat it, compare this to the original images, what's different? And then when you get what's different, the way backprop works, it says, okay, this pixel fails, this pixel fails, this pixel fails. Like these should be red, not green. This one should be blue, not green, exactly. So it tells you the error rate for every single picture. So after we splat it, then we need to be able to take that information and turn it back into where the Gaussians are and what's wrong with them. And so it's like, if this red pixel is wrong, why? And that's what's called the backward pass. So we propagate our gradient back from this rasterization, and we want to basically unsplat it and say, okay, this pixel has this flaw by this amount because of this Gaussian. And so then our learning rate can go boop and can kind of move that Gaussian around. So there was a bunch of fast renderers on the Mac. There wasn't a lot of libraries that had fast backwards and forward. And so PyTorch, which I'm sure anyone knows if they're doing machine learning, is the standard library for doing fast forward backward. It has this magical thing called autograd, where if you just write the forward pass, it gives you the backward pass for free because it automatically does a gradient for you. This works really well in like almost every case. It's kind of amazing. And generally writing backwards yourself is like really painful and way slower. And so you just let PyTorch handle it and you use PyTorch compiler and it's like kick-ass for you. But Gaussian splats is actually, funny enough, one of these cases where that just completely falls apart. And so the reason is, you have all these pixels, and so PyTorch generally works on giant matrix multiplies for like LLMs or CNNs, and it's like take every pixel, run a bunch of NLPs on them, do that, decode it, uncode it, and it's like it's just to take a huge array of numbers, do math on all of them, take the next step, take the next step. Gsplats has this kind of random memory lookup thing where it's like we have all this big pixel buffer and we want to work with all of them, but there's like a million different splats and we don't know which one lines up to which pixel. And so PyTorch will just naively do your backwards across all of your pixels for all of your Gaussians, and it ends up costing you 66,000% more runtime. Or if you try to do more splats, it just completely, like the Kier is 65,000% slower to do it in PyTorch versus this library I wrote for 512, and it's like, that's just not doable. So like this, you can run it as many steps as you want and train really quickly, like that script I showed you. Why can we do this in a minute? If you would do PyTorch, it would have taken like 3 hours or something. And then if you try to do more splats, actually, you just run out of memory like really, really fast because of this explosion kind of thing that I'm talking about. And so you can see this here. If we do 64,000, what are we at? It's 100,000 times slower. And so it's, instead of doing it in speeds of milliseconds, we're doing it in speeds of, how many seconds or minutes does this thing take? And it's just not even feasible. So I wrote this library, fast Mac gsplat, and if you like doing world model research and training world models and training splats, should be useful for you. There's a bunch of different versions, and then I kind of iterated on, if you look in, there's like Metal V7, V6, V4, and I just kept squeezing more and more speed out of it. There's probably some I didn't even publish now as well, but this makes it possible to just kind of explore and train models locally on your machine. So I think if you want to scale up and you're doing, something for production and you have 100 GPUs and you're going to train a model, which eventually I will. And so I'm going to say, okay, I want to spend a bunch of money and I want to pre-train my whole model. I'm going to go to CUDA and I'm going to go to NVIDIA and I'm going to use, their kernels. But in the meantime, these Macs are really fast. And so this is super duper fast. And if you're doing experiments like we are, where let's just say instead of buying a cluster of 8 GPUs that cost $500,000, I'll just make the image tiny and run baselines on my computer. What this lets me do is run experiments locally on my Mac. And so I can just, like we're doing now, try stuff, iterate, see what works and doesn't work before I go to scale up. So all of the exploration is cheap on my Mac, thanks to this library. It also means people like you can just clone this thing, run it on their Mac, and get it going fast. And so, I'd love people to fork this, add it for Windows if they need it for their weird AMD shaders or whatever. But here's a list of the different variants in there. And I kept them all there kind of for posterity, but also because Codex learns really well from its prior failures. So if you can say, here's the 7 different shaders we wrote, and write a new one that takes into account all of the old failures and all of the new learnings we have, it can do really well for you. There's still some real speed wins on the table, even though it's 10 milliseconds for 64,000 splats. We can do way better. Like, you can go to millions of splats in 10 milliseconds. So the way you do that is hardware rasterization. I started a bit about this. V7 finished hardware starts to do this. And so basically in your Mac card, if you go into like the metal kernel shell documentation from Mac, they'll tell you like, we have this thing that can render splats instantly for you. You don't even have to write any of your own metal code. And so you can take these little image shaders and you can use those, and it'll use the exact hot path right on your hardware that renders and rasterizes 3D objects. It's a little complicated. How do you combine that fast rasterizer with forward and backward passes that are fast? Because that thing is meant to just render. It's not meant to track the gradients and to save intermediate states, so you can kind of find out what those gradients were. But I've been working on trying to get those to kind of merge together, because there's some very cool papers that do this for CUDA and for NVIDIA and speed it up as well. So super easy to use. Look at this, it's like nothing. You just import it and call it, and it's rasterized. So you pass in, here's my config, and then you pass in, what are my means of my Gaussians, conics, colors, opacities, depths. So just pass in all your Gaussians and render them, and you get an image. It's got documentation. You can point your agents at it. Here's a little bit bigger that shows like, here's a bunch of random Gaussians, so random colors, random opacities, random depths, and then rasterize all these random things. Just one of the many little things that I've been plugging away at to get this training repo working so I can do cheap rendering. But let's go back to our agents. I think Codex is slow because metal shaders just take a while. But it looks like it's starting to add a README, and it's got V5 features, and it even ran a throughput sweep for us, which I did not ask for because that takes a while. But this is pretty awesome. If we look at the numbers here, Codex was able to write a rasterizer for us, and it only takes 36 milliseconds compared to